Hello dear students, welcome to this program. Today we are discussing an interesting topic which is glucose and fructose open chain and cyclic structure. The main objectives to understand are determination of configuration of monosaccharides, absolute configuration of glucose and fructose, what is Demuta rotation and what is ascending and descending in monosaccharides. Before discussing our first objective, let us understand what are the carbohydrates. Carbohydrates or saccharides in Greek is derived from saccharon, meaning sugar, which are the essential components of all living organisms and are in fact the most abundant class of biological molecules. The name carbohydrate, which literally means carbon hydrate, stems from their chemical composition, which is roughly C.H2ON. Here C stands for carbon and H2O stands for water, where N is greater than or equal to 3. Many but not all carbohydrates have the empirical formula C.H2O whole N. Some also contain nitrogen, phosphorus or sulfur. The basic units of carbohydrates are monosaccharides. Carbohydrates are polyhydroxyaldehydes or ketones or substances that yield such compounds on hydrolysis. Major classes of carbohydrates: monosaccharides, disaccharides, oligosaccharides and polysaccharides. Monosaccharides are single sugar unit molecules, while as the disaccharides contain 2 sugar units. Oligosaccharides contain 3 to 10 sugar units and polysaccharides contain more than 10 units. Coming to first class of carbohydrates, monosaccharides. Monosaccharides are colorless crystalline solids that are freely soluble in water but insoluble in non-polar solvents. Most have a sweet taste. The backbones of monosaccharides are unbranched carbon chains in which all the carbon atoms are linked by single bonds. The two families of monosaccharides are aldoses and ketoses. Monosaccharides or simple sugars are aldehyde or ketone derivatives of straight chain polyhydroxy alcohols containing at least 3 carbon atoms. Such substances, for example, D-glucose and D-ribulose, cannot be hydrolyzed to form simpler saccharides. Monosaccharides are classified according to the chemical nature of their carbonyl group and the number of their carbon atoms. If the carbonyl group is an aldehyde, as in glucose, the sugar is an aldose. If the carbonyl group is a ketone, as in ribulose, the sugar is a ketose. The smallest monosaccharides, those with 3 carbon atoms, are trioses like glyceraldehyde, which is an aldotriose, and dihydroxyacetone, which is a ketotriose. Those with 4, 5, 6, 7, etc. carbon atoms are respectively named as tetroses, pentoses, hexoses, heptoses, etc. These terms may be combined so that, for example, glucose is an aldohexose, whereas ribulose is a ketopentose. The hexoses, which include the aldohexose D-glucose and the ketohexose D-fructose, are the most common monosaccharides in nature. The aldopentoses D-ribose and 2-deoxy-D-ribose are the components of nucleotides and nucleic acids. Now the first objective, which is open and closed structure of glucose and fructose. D-glucose is the aldohexose because it contains an aldehyde group CHO at the top first carbon, that is at position 1, and is a monosaccharide with 6 carbon units in total, thus is a hexose. D-fructose, on the other hand, is a ketohexose because it contains a ketone group C double bond O and is a monosaccharide with 6 carbon units in total, thus is a hexose. Closed structure of glucose and fructose. Pentoses and hexoses cyclize to form furanose and pyranose rings. The predominant forms of ribose, glucose, fructose and many other sugars in solution are not open chains. Rather, the open chain forms of these sugars cyclize into rings because the ring forms are energetically more stable. The basis for ring formation is the fact that an aldehyde can react with an alcohol to form a hemiacetal. For an aldohexose such as glucose, the carbon 1 aldehyde in the open chain form of glucose reacts with the carbon 5 hydroxyl group to form an intramolecular hemiacetal. The resulting 6-membered ring is called a pyranose because of its similarity to pyrene. Similarly, a ketone can react with an alcohol to form a hemiketal. For a ketohexose such as fructose, the carbon 2 keto group in the open chain form of fructose reacts with a hydroxyl group within the same molecule to form an intramolecular hemiketal. The carbon 2 keto group can react with either the carbon 6 hydroxyl group to form a 6-membered ring or the carbon 5 hydroxyl group to form a 5-membered ring. The 5-membered ring is called a furanose because of its similarity to furan. Our second objective is determination of configuration of monosaccharides. All the monosaccharides except dihydroxyacetone contain one or more asymmetric chiral carbon atoms. Chiral carbon means a carbon which is attached to 4 different groups and thus occur in optically active isomeric forms. The simplest aldose, glyceraldehyde, contains one chiral center, the middle carbon atom, and therefore has 2 different optical isomers or enantiomers. Sugars that differ only by the configuration about one carbon atom are known as epimers of one another. Thus, D-glucose and D-mannose are epimers with respect to carbon 2, whereas D-glucose and D-galactose are epimers with respect to carbon 4. However, D-mannose and D-galactose are not epimers of each other because they differ in configuration about 2 of their carbon atoms. D-glucose is the only aldose that commonly occurs in nature as a monosaccharide. However, it and several other monosaccharides including D-glyceraldehyde, D-ribose, D-mannose, D-galactose are important components of larger biological molecules. Fischer projection formulas. Glyceraldehydes contains a chiral center and therefore exists as a pair of enantiomers. Glyceraldehyde is a common name. The IUPAC name for this monosaccharide is 2,3-dihydroxypropanol. Similarly, dihydroxyacetone is a common name. Its IUPAC name is 1,3-dihydroxypropanone. The common names for these and other monosaccharides, however, are so firmly rooted in the literature of organic chemistry and biochemistry that they are used almost exclusively to refer to these compounds. Chemists commonly use 2-dimensional representations called Fischer projections to show the configuration of carbohydrates. Following is an illustration of how a 3-dimensional representation is converted to a Fischer projection. The horizontal segments of a Fischer projection represent bonds directed towards U, and the vertical segments represent bonds directed away from U. D and L monosaccharides. Even though the RS system is widely accepted today as a standard for designating configuration, the configuration of carbohydrates as well as those of amino acids and many other compounds in biochemistry is commonly designated by DL system proposed by Emil Fischer in 1891. At that time, it was known that one enantiomer of glyceraldehyde has a specific rotation of plus 13.5. The other has a specific rotation of minus 13.5. Fischer proposed that these enantiomers be designated D and L for dextro and levorotatory, but he had no experimental way to determine which enantiomer which specific rotation. Fischer therefore did the only possible thing. He made an arbitrary assignment. He assigned the dextrorotatory enantiomer an arbitrary configuration and named it D-glyceraldehyde. He named its enantiomer as L-glyceraldehyde. Fischer could have been wrong, but by a stroke of good fortune he was correct, as proven in 1952 by a special application of X-ray crystallography. D and L glyceraldehyde serve as reference points for the assignment of relative configuration to all other aldoses and ketoses. The reference point is the chiral center farthest from the carbonyl group, because this chiral center is always the next to the last carbon on the chain. It is called the penultimate carbon. A D monosaccharide has the same configuration at its penultimate carbon as D glyceraldehyde. Its OH is on the right when written as a Fischer projection, and L monosaccharide has the same configuration as its penultimate carbon as L glyceraldehyde. Its OH is on the left. Haworth projections. A common way of representing the cyclic structure of monosaccharides is the Haworth projection, named of the English chemist Sir Walter and Haworth, who was awarded a Nobel Prize for Chemistry in 1937. In a Haworth projection, a 5 or 6 membered cyclic hemiacetal is represented as a planar pentagon or hexagon, as the case may be, lying perpendicular to the plane of the paper. Groups bonded to the carbons of the ring that lie either above or below the plane of the ring. The new chiral center created in the forming the cyclic structures called an anomeric carbon. Stereoisomers that differ in configuration only at the anomeric carbon are called anomers. The anomeric carbon of an aldose is carbon 1. That of the most common ketoses is carbon 2. Haworth projections are most commonly written with the anomeric carbon to the right and the hemiacetal oxygen to the back. In the terminology of carbohydrate chemistry, the designation beta means that the OH on the anomeric carbon of the cyclic hemiacetal is on the same side of the ring as the terminal CH2OH. Conversely, the designation alpha means that the OH on the anomeric carbon of the cyclic hemiacetal is on the opposite side of the ring as the terminal CH2OH. In anomers, it is important to notice that the furanose or pyranose of a carbohydrate has one more asymmetric carbon than the open chain form carbon 1 in the case of the aldoses. Thus, there are two possible diastereomers of D-glucopyranose. Both of these compounds are forms of D-glucopyranose, and in fact, glucose in solution exists as a mixture of both. They are diastereomers and are therefore separable compounds with different properties. When two cyclic forms of a carbohydrate differ in configuration only at the hemiacetal carbons, they are said to be anomers. In other words, anomers are cyclic forms of carbohydrates that are epimeric at the hemiacetal carbon. Thus, the two forms of D-glucopyranose are anomers of glucose. The hemiacetal carbon, carbon 1 of an aldose, is sometimes referred to as the anomeric carbon. As the preceding structures illustrate, anomers are named with the Greek letters alpha and beta. This nomenclature refers to the Fischer projection of the cyclic form of a carbohydrate, written with all carbon atoms in a straight vertical line. In the alpha anomer, the hemiacetal OH group is on the same side of the Fischer projection as the oxygen at the configurational carbon. The configurational carbon is the one used for specifying DL designation, that is, carbon 5 for the aldohexoses. Conversely, in the beta anomer, the hemiacetal OH group is on the side of the Fischer projection opposite the oxygen at the configurational carbon. Coming to the term mutarotation, isomeric forms of monosaccharides that differ only in their configuration about the hemiacetal or hemiketal carbon atom are called anomers. The hemiacetal or carbonyl carbon atom is called the anomeric carbon. The alpha and beta anomers of D-glucose interconvert in aqueous solution by a process called mutarotation. Thus, a solution of alpha D-glucose and a solution of beta D-glucose eventually form identical equilibrium mixtures having identical optical properties. This mixture consists of about 1/3 alpha D-glucose, 2/3 beta D-glucose, and very small amounts of the linear and 5-membered ring glucofuranose forms. Ketohexoses also occur in alpha and beta anomeric forms. In these compounds, the hydroxyl group at carbon 5 or carbon 6 reacts with the keto group at carbon 2, forming a furanose or pyranose ring containing a hemiketal linkage. D-fructose readily forms the furanose ring, the more common anomer of this sugar. In combined forms or in derivatives is alpha D-fructofuranose. The mutarotation of glucose is caused by the conversion of the alpha and beta glucopyranose anomers into an equilibrium mixture of both. The same equilibrium mixture is formed as it must be from either pure alpha D glucopyranose or beta D glucopyranose. Mutarotation is catalyzed by both acid and base, but also occurs even in pure water. Mutarotation is characteristic of the cyclic hemiacetal forms of glucose, and aldehyde cannot undergo mutarotation. Mutarotation was one of the phenomena that suggested to early carbohydrate chemists that aldoses might exist as cyclic hemiacetals, ascending and descending in monosaccharides. The ascending series in monosaccharides is the conversion of pentoses into hexoses, and the descent series in monosaccharides of the sugar series is the conversion of hexoses to pentose sugar units. Now discussing the ascent of the sugar series, that is conversion of pentoses into hexoses. First one is Kiliani cyanohydrin synthesis. This reaction is used for ascending the series. The sugar is treated with hydrogen cyanide HCN to give the cyanohydrin, which is then hydrolyzed to give the acid, then lactonized and reduced. The mixture of cyanohydrins can be converted into a mixture of aldoses by catalytic hydrogenation, and these aldoses can be separated. In the previous reaction, a new asymmetric carbon atom is formed, and one would expect equal quantities of the epimers would be formed, but this is not the case. One of the two isomers predominates usually, that is because the starting material is optically active, and the reaction is therefore an asymmetric synthesis. The Kiliani reaction has been used to prepare sugars having 10 carbon atoms. Second is the nitromethane synthesis, Sowden-Fischer synthesis. Another method of extending the length of the carbon chain involves the base catalyzed condensation of nitromethane with an aldehyde to produce a C-nitroalcohol and decomposition of the sodium salt of the latter with cold mineral acid to give an aldehyde containing one more carbon atom than the original aldehyde. The reaction is usually carried out in methanol with sodium as basic catalyst. As in the cyanohydrin synthesis, two epimeric products are formed. The mixed epimeric C-nitroalcohols are readily separated by fractional crystallization, and decomposition of the sodium C-nitroalcohols gives the higher sugars in good yield. Sowden by the above method, but using 2-nitroethanol instead of nitromethane, converted an aldose into a ketose containing 2 additional carbon atoms. Third one is the diazomethane synthesis. The action of diazomethane on an acid chloride to give a diazomethyl ketone has been employed in Ascent of the sugar series. Now the last objective of our topic, that is descent of the sugar series, that is conversion of hexoses to pentoses. First is the method of Hall. This method consists in converting the aldose into oxime, which on treatment with acetic anhydride is converted into the nitrol and acetylated. On treatment, this nitrile acetate with ammonical silver oxide, a splitting hydrogen cyanide takes place together with the hydrolysis of the acetate groups resulting in the lower aldose sugar. An intermediate of the last reaction usually obtained, which is an addition product of acetamide and the sugar. This is readily hydrolyzed with acid. Second is the method of Ruff. This method consists in oxidizing the aldose to aldonic acid and reacting its calcium salt with hydrogen peroxide in the presence of ferric salt to give first an intermediate alpha keto acid, immediately decomposes giving carbon dioxide and lower sugar. Here we come to the conclusion of our today's topic. Hope you understood it well. Thank you.